Welcome back to part 2 of the PowerPoint on pre-engineered metal buildings. As a review, we went through types of buildings that can be pre-engineered metal buildings. We talked about the differences between pre-engineered metal buildings and structural steel buildings. We talked about the different parts and pieces of a pre-engineered metal building, and we talked about loading on pre-engineered metal buildings and the different types of loading. We went through the rigid frame section, identifying all the parts of a section through a pre-engineered metal building. And then we talked about anchor bolt plans and how to set those up. We also went over the detail sheet, and then I went over the first part of the assignment with you. So today we are ready to start on the second part of the PowerPoint and the second part of the assignment. So the first thing we're going to talk about is the rigid frame cross sections. Rigid frame consists of the columns that are attached to the floor, which is typically a concrete slab, by anchor bolts, and then the beams are attached to the columns, so it forms a frame. A cross section through the building shows the configuration of the building. If you look on this slide, you can see that it shows the perimeter columns, it shows some interior columns, and then it shows the main beams that run across the top. Coming at us, towards us in a direction, are the purlins. If you look in the wall itself, you can see the girts. So on doing rigid frame cross sections, the dimensions are selected by the drafter from the chart on page 139 that we looked at last class. The dimensions for various widths and heights are pre-engineered, so we have to work within those requirements that the pre-engineered metal building supplier provides us. So there will be some variation between different manufacturers. Again, this is the chart from page 139 in your book. There are two types of buildings listed here. PSE stands for primary structural element. LL stands for live load. The 20 PSE LL, which is the live load, and the 30 PSE live load. And then you base it off of the width, the height, and that determines the B, C, and E. And if you look at the chart on the right-hand side, you'll see what represents each of those letters. Rigid frame sections come in a variety of designs. Some of them are like what you saw in that picture, and others are maybe formed a little differently. So again, each individual design has its own set of pre-engineered calculations. That's why you can't assume working with one manufacturer is going to be the same as the other, because they're all a little bit different. Here is an example of that. We have the top one that is basically one slope, and the bottom of the rafters or the main beams are equal. In the one below, you see that the shape of the bottom of the rafters or beams are also different. So again, depending on what manufacturer you're using, each one is going to be a little bit different. So how do we go about drawing the rigid frame cross section? First, we have to find out the appropriate cross-sectional configuration from the manufacturer. Then we go to the chart of the pre-engineered dimensions for the cross-sectional configuration and find the height and the width of the building, and then the weight of the steel. Lay out the rigid frame cross-section and add all the necessary dimensions. The next part of the pre-engineered building, after we get the frame in place and we get it connected to the floor slab with the anchor bolts, is we start putting on the remainder. So here is an example of a roof framing plan. If you see running up and down, you'll see a line that represents the main beams, and you'll see there are some grid lines there, 1, 2, 3, and 4. Then running in the opposite direction, you'll see an A, B, C, and D, and that is where the columns are also located. Members that are running from left to right are the purlins, and they are setting on top of those beams that we see at 1, 2, 3, and 4. You see some dashed lines in that center section. That is cross bracing. That is designed by an engineer or the pre-engineered metal building company, depending on where it's located. That is just some additional support in that area that they feel is necessary to help keep the building structurally sound. So how to draw the roof framing plan? Again, you start with your anchor bolt plan, the rigid frame sections, and any instructions or sketches provided by the engineer. You'll lay out the column grid for the length and width of the building, just like we kind of did the other day, only we just Laying out the anchor bolts was the main purpose for that. We will determine the spacing for the purlins that will be attached to the roof beams. Typically, an engineer will provide the spacing. Lay out the purlins according to spacing. Typically, an engineer will determine the distance that purlins extend beyond the columns, and then add the necessary dimensions. Now we have basically the entire frame. We have the floor slab with the anchor bolts connected to the base plate of the columns connected, the columns connected to the main beams, and then we have the purlins and the girts placed. The girts are placed in between the columns on the walls, and the purlins are placed on the roof. And so our building is basically now all tied together. But to finish it, we have to put the exterior onto our building, and that is called sheeting. So this one is a roof sheeting plan, and it shows the length of the sheeting panels for the roof. And you'll notice there's a space in between those panels. The reason for that is there is usually, you need to allow for expansion and contraction, plus that's usually where venting goes on top of the roof. So that will have probably a roof vent that runs across there and closes off the top of the roof. You'll notice that they are divided up equally into 2'6" panels, except for on the ends, and they are noted as 2'3" panels. Again, typically, and our book is not the best book, but each one of these would be labeled with a number, so it would be very easy to know where they go. The 2'3" panels on each ends are the ones that they will cut to fit on site. The others, they should not have to do any cutting to make those fit. So to draw the sheeting plan, use the roof framing plan and any instructions provided by the engineer's guides. Determine the length of the sheeting panels, include the overhang. Determine the spacing for the sheeting panels. Typically, an engineer will provide the spacing. Lay out the sheeting panels according to spacing pattern. Add the necessary dimensions from that point. Then we go and we add the sidewall framing plans. Again, this is going to show where the eave strut is on this particular one. You'll see these are the side panels, and then it's going to show the girt in the wall. You may have additional girts at door openings or window openings, etc. And it will give you the height of where the girt is placed, and it will give you the height of where the eave strut is placed. Again, they are missing their column grid lines on here. They've noted the edge of the concrete slab, and they have noted how far the first column sits off of the edge of the slab. You will also see there is a dashed line that is running diagonally in the center bay. That again is going to be some cross bracing that's going to be added, and that is typically designed by an engineer. Typically, a sidewall framing plan has very little detail. You'll notice there's no thickness to the columns, no thickness to the girts, that sort of thing. With our section that we're going to do, we're going to actually show a full section. Single lines are usually used to show the spacing of the columns, shows the location vertically of the girts and eave struts. It is understood that base angles are located at the top edge of the concrete slab. The sheeting plans. Now this one does have some numbering on it. You notice that panels 1 are on each end and panels 2 are in the middle. Again, panels 2 would be equal dimensions. Panel 1 would be the leftover pieces and enough that they can cut those on site to make them fit. It shows the numbers of panels in their arrangement. Length and width of panels are pre-calculated. Again, there is information missing off of here. On our building, we are not going to do the sheeting plans, but you need to understand how they work. The end wall framing and sheeting plans, the same rules and practices apply, but you'll notice you have multiple pieces that are not all the same, because this is where the roof actually slopes, so those pieces will have to be cut to fit on site. You have some pieces that are sticking out on each side. Those are the end panels where they make the corners. Again, we have some cross bracing in the middle section, and again, that is for additional structural integrity. The last thing that we have to do is we have to do some enlarged details. We need to know how this particular manufacturer's building goes together. So there's 3 connections that we will do. We'll do a girt connection, a purlin connection, and an eave strut connection. Girt connection details show how the girts are connected to the columns. Typically involves bolting the girts to the girt clips. Shows the connection, bolting spacing, and dimensions and size of bolts. And the information is provided by the engineer, but the drafter will typically know after doing drawings for a while. If you are working with the same manufacturer and same type of buildings all the time, you become very familiar with what's going to be required, and a lot of times you already know, and then the engineer just reviews what you have done. The purlin connections shows how the purlins are connected to the rafters. Typically involves bolting again the purlin to the rafter, overlapping purlins and bolting the overlap purlins. They show the connection amount of overlap between purlins and bolt spacing, because purlins, we can't go the full distance, so they have to connect them because they can only be a certain length. And so you want to make sure that that purlin overlaps the other purlin so you have a good connection there. The information is provided by the engineer, but again, after you've been doing this for a while, you will already know what that needs to be. The eave strut, this is the edge that goes along the low side typically of the building. You need to show how it's connected to the rigid frame. The eave strut connected at the column or to an eave strut bracket that is connected to the column by a shop weld, meaning that bracket will already be on the column when it comes to the job site. Again, we try not to weld in the field if we can help it. So where those eave strut brackets go, those will be pre-welded in the shop. And the information again is provided by the engineer, but the drafter will typically know after doing drawings for a while. So that is the end of the PowerPoint. So the next part, we will go over the class instructions for this particular assignment, and then we will get into drawing it together like we did on the last one.